That sounds like me. No problem. Which brings up a very good question. Do I actually have to be here to teach this class? Because I have recordings from 2016 and a few semesters before that too. So it's on YouTube. Yep. Okay, let me show you guys how to find it. Well, okay, that was a snafu on my part. Okay, so let me just show you how to find the lectures of this class. So if you just search for cisp300, most likely than not, you'll be finding my stuff. And you can find stuff that is dated all the way back to 2011 and 2010. And each one, I think, is a full semester recording too. So,
really fleshed out, good detail, probably.
Well, it's exactly the way I taught that class in lecture.
Wouldn't it be scary if it's like one to one, if everything you say is wrong?
Oh, that would bore me to death. I can't do that. If I were to do that, I might as well just play the video instead of teaching the class, right? so I can actually do something else. Okay. So just so that you guys can find like recordings all the way back to 2000. I think 2011 is the earliest, possibly. I think this is actually. I think we found a little one that is even earlier. Maybe not. But anyway, I'll let you guys try to find all that stuff. All right, the recorder should be on. Let me just double check. Yep, it's on. Audio is on too. Are there any questions about the homework assignment? Okay, so I see some people nodding. Yep, go ahead.
When we're tracing it, do we have to show the different values in the array since they aren't changing?
The trace should include those in columns, but you don't have to change those columns.
Okay.
Yep. Because they are technically still variables, except in this particular algorithm, we are not changing. So you still have to have columns representing them. Yep.
So that when we imagine that it's initialized precondition is still something within our
Right.
we don't have to show that in the trace, right?
You do, but that's the whole point. That's what he's asking. So in the trace, each array element needs its own column, even though they're not changing.
So if they have their own column, but we can't show that over here on this other side, though, where all the comments are at?
You do not need to show them on the comment side. You just have to show them in their own columns on the right-hand side.
Could you quickly show us what the code for that would look like?
I think I might have shown you one. Okay, let's see if the notes has one.
To initialize it to 6 elements?
Okay. Okay, so the note doesn't give you an actual trace, but I think last time we did at least one of those traces. I think we did one trace, of how to search.
I think on Wednesday.
On Wednesday?
Last week I was checking.
Okay. So basically it would be the same format, where the array needs to have one element per column. And the ordering between your other variables versus the array is not important as long as they're all in the trace. We'll do some traces today with arrays, so maybe that will answer your question.
Well, I just wondered what the initial code to initialize the array would say.
There's no code to initialize the array. The values in the array is in the precondition. It is just given to you. Okay? Well, I'll show you an example, because if we get to binary search, we'll get to that, that kind of code too. All right. So I added a little bit more to the website. So if you go to the website, I added just a little bit more on subroutines. So that thing you might want to read because there'll be some lecture material on Wednesday, but this is kind of a big topic. So when you go to the class website, this is new, okay? Subroutines, invoking and returning. And this is representing a whole different concept compared to what we are studying. This is in addition to what we have already been studying, but it is a concept that is, I would just call it orthogonal to what we have been talking about. So that's kind of important.
Call it what?
Huh?
Call it what?
Calling and returning a subroutine, or invoking and returning from a subroutine. So it talks about subroutines. So we'll get to it hopefully on Friday at the latest. So what we'll do today is to continue to talk about searching in a sorted array, and we'll talk about binary search. But before I go there, I just want to see if there are any questions I can answer about the homework assignment, which is due on Wednesday, of finding the longest run. So do you guys have the idea of how to do it, like the logic of the code to do it? There are several ways to do it, okay? Okay, I see some people turning their heads. So how far did you guys get? Done, okay. So how about you guys? Not very far. That is not a very specific answer. Yep, go ahead.
I missed Friday and I'm halfway through last episode.
It is kind of an episode. Yep.
So I'm still kind of lost on that, but if we're going to be doing searching through sorted arrays, then if that's similar to how to find the longest run is.
It is not exactly the same thing. So let me just kind of spend a little bit of time on how to find the longest run, and then we'll move on and go back and talk about how to do binary search. Okay, so even if you have found an algorithm to do it, there are many ways. There are a few ways to do it. So I'll just go ahead and explore that. That is assembly code. Yep, go ahead.
So I know for me, I tried to write the pseudocode from just human language and then tried to make values and stuff out of it.
Mm-hmm.
And that got me started, and then I went into, I started writing the code next to a trace table, and then started tracing out the code as I was writing it, and that seemed to really, really help.
Okay, that's good to know. So the first thing we need to do, for those who are having a little bit more difficulty getting it started, is to do an example by yourself. Okay, so we'll go ahead and start with an example. So we have 2, 3, 3, 1, 5, 3, 5, 4, 3. Okay, so there we go. I'll maybe make it 3, 3, 3 here. Okay. So the approach is, this is easy peasy. So you can just kind of imagine that you should only look at one or two elements at the same time, okay? There are several ways to do it. You can basically use a double loop where the first index starts with a particular element, and then the second index would look from the next index up and go like, is this the same as the first one? If so, is that also the same as the first one? If so, if that is the same as the first one, until you either hit the end of the array, then you have to stop, or you find something that is different, then you also have to stop. So that's one way to do it, is to have a nested loop, a while loop inside a while loop. That's one way to do it. The second way to do it is to look at a particular element and say, am I continuing a run? In other words, you look at the one that's before and say, am I continuing a run? In this case, it's definitely not, so you have to reset the counter to 1, because 1 is the minimum number of a run, a minimum length of a run. Then you move on to this one and go like, am I continuing a run? The answer is yes, I am continuing a run because the one before has the same value, so I'm continuing a run, which means I increment the counter instead of resetting the counter. Then you move on to this one, and you say, am I continuing a run? The answer is no, because 1 is different from 3, so you reset the counter to 1 in this case. And then you move on to here, am I continuing a run? Nope, you reset the counter to 1, even though it's already 1. Am I continuing a run? No. Am I continuing a run? No. Am I continuing a run? No. Am I continuing a run? Yes. Increment the counter instead of resetting it to 1. Am I continuing a run? Yes. Increment the counter instead of resetting it. But every time you increment the counter, you kind of have to say, oh, but is this longer than the longest run that I have seen already? If it is, I'm going to have to reset that too, because I'm supposed to keep track of the longest run or the length of the longest run. Yes?
So that actually becomes important, even though your code or your elements didn't exhibit that, it still needs to include that concept in the code that we wrote, right? So in other words, your code only has 2 pairs, but the stuff you wrote on the board has 3, but our code needs to be able to recognize the fact that it could need to reset later, right?
Your code needs to make it work in general. So no matter what pattern or what kind of array I give you, it still has to work. And so there are 2 ideas to do it. One is to have a double loop. So you have the outer loop controlling where you're starting, and then the inner loop to controlling how far can I push this run. Okay. The other one is simply to look at each number individually and compare it to the number before to see whether you are continuing a run. So both methods will work. I'm not looking for the most efficient way to do it. So as long as your method is correct, you will get full credit. Okay?
So we can write lazy pseudocode in this class?
You can write lazy pseudocode that logically makes sense. Yes. You can be as lazy as it still makes sense to me. All right? So do we have any other questions about the homework assignment? Nope. All right. Well, if there are no questions about this homework assignment, we'll go ahead and start with binary search again. Okay, something that we have talked about already in the previous class. So, so with this one, I think I have talked about this approach many times. The best way to do it is to give yourself an example that it is difficult to eyeball. Okay, you just cannot look at it and go like, yep, we know what the answer is. But that would require a lot of samples. So in this case, I'm just going to use a slightly longer example, and then we'll go ahead and work with this one today. So it has to be a sorted array, because binary search only works when you know how an array is sorted. Yep.
So the elements have to be contiguous. What is the definition of sorted? Is that in numerical order or grouped according to however the array is supposed to be arranged? What is the difference between
in this case, it's not.
And a sorted array?
So in this case, it just has to be in a non-decreasing order. The assumption it is in a non-decreasing order, because you can look at 2 is less than or equal to 5, 5 is less than or equal to 16. You can have duplicate values. It will still work. Binary search will work when your array has duplicate items.
So that's a sorted array.
That is a sorted array.
What if it was from greatest to least but still in numerical order?
You can do that, but your algorithm would be different. In other words, it will still be considered sorted, but how your array is sorted affects what kind of comparison you need in order to get it to work.
So the example of an unsorted array would be the values of the elements in the longest run assignment, out of order.
That is out of order.
Okay, that's unsorted?
That is, if you find at least one element that is out of order, it is not sorted. Okay? All right. So in this particular case, let's say we want to find, okay, what value do you guys want me to find? Give me something that you think is going to be tricky, even something that is not even a part of these 7 numbers. We'll go through a few runs. So give me a number now, and I'll use another number later on. You can, huh? 73. 73 and 3. So I'll just go ahead and say 73, and then later on we'll get back to 3. Okay. So we'll search for 73 first. So the way we do it is we find the element that is right in the middle of the entire thing. And this one turns out to be exactly at the center, because we have 7 elements. And when you have 7 elements, the 4th one is right in the middle of the entire array. So we now compare 73 to 89, and we go like, what is the relationship between 89 and 73? 73 is less than 89, okay? Any questions about this relationship? Okay, But what does that mean? Well, it means one thing rather obviously. It means this element is not what we're looking for. That's the first thing that we know. But because the array is sorted, it also tells us that everything after this is also going not to match what we're looking for. Is that making any sense? Yep.
If you have an array that had an even number of elements,
Well, we'll deal with that later. So for now, we focus on just this one. Okay?
does binary search apply to only arrays that have an odd number of elements?
No, we are just working through an example. So right now we're not writing pseudocode. We are just working out an example. Because until we can do it by hand, there's no way we can actually code it in the program. So we'll work it out by hand first. All right, so what is the conclusion of this? Well, the conclusion of this comparison is not only that 89 is greater than 73, but we also know every single number after that is also greater than 73. Okay, so there's no easy way to say it, so I'm going to have to use that trick. Is that okay? Does it make sense? But this conclusion can only be made if the array is sorted. If the array is not sorted, I can't make that conclusion, right? So what is the subproblem now? The subproblem now is, oh, we only got three elements left that may be 73. So out of these three, I find the one that is in the middle, which is this one here. And then I ask, how do you relate to 73? We go like, it is less than 73. But then we also know everything that is above it is also going to be less than 73 because the array is sorted. Is that making any sense? So the only portion of the array that can contain the value that we are looking for is only this part now. So now we compare 73 with this element, which has a value of 16, and we go like, 16 is less than 73. Now, of course, that also automatically says everything above is also less than 73, which we already know from earlier. So now, when you look at every single element in the array, they are not 73. They're either greater than 73, or they are less than 73, which means 73 is not in the array. Okay, so that's one example. Do we have any questions about this particular example, how we come to the conclusion that 73 is not in the array? Yes? Oh, okay, all right. So the next one is, yeah, go ahead.
Well, it just occurs to me that so we just take a value and we're just trying to see if we can find it in the array.
That's what we are trying to do. Yep. Searching for a particular value in an array. All right, so let's try another example. We'll use exactly the same array. Okay. And I'm just going to scroll down a little bit and present it here. This time we're looking for the value 3. So let's go and find out how we can figure out that 3 is not actually in the array. Same as before, we look at everything and we say, what is the middle of the entire array? 89, or the element with a value of 89 is in the middle. So we now look at 89 and we look at 3 and say, do they equal to each other? If not, who is greater? Well, that's pretty easy to confirm that 89 is greater than 3. But 89 is greater than 3 also means that everything after that is also going to be greater than 3. Because the array is sorted. Is that making any sense? All right, so now we can make this conclusion and say that everything after 89 is also going to be greater than 3, which means I can rule them out right now. I got 3 elements left that can potentially be 3. I look at these 3, I find the one in the middle, which is this one here, and I make a comparison. This is my second comparison, which confirms that 5 is greater than 3 as well. So because 5 is greater than 3, we can also conclude that everything after this is also greater than 3. And this is reconfirming those 4 values are greater than 3, but that's fine. It's not going to hurt. Now we only have one element left, which is 2, and then we ask the question, how does that relate to 3? We do this one final comparison, and we say 2 is less than 3. Fine. But now we have also ruled out every single element because they are either greater than or less than 3. So we know that 3 is not in the array. Is that okay? Does anyone want another value? What about 121 or 1? Yep. 101. All right, so let's go try 101. So once again, we copy and paste this entire thing. So going through all of these examples by hand is going to give us some insight of how to write the code. In other words, what we are trying to do is to generalize what we are doing so that we can actually write it out as pseudocode. What was it again? 101? Yeah. Okay. All right. Same thing. We look at, because at first, the entire array is not ruled out. So any one of the 7 elements can contain the value that we are looking for. But out of the entire range, we look at the one in the middle. So we are always looking into the middle and say, okay, how does 89 compare to 101? We say, well, 89 is less than 101. But that means everything before that is also less than 101. So now we can rule out the first 4 elements as potential choices for 101. Now we only have 3 left. We look at these 3 remaining and ask which one is in the middle. Well, fortunately, 101 is right there in the middle. So now we say, oh, okay, great. We just found 101. And it doesn't let me enter the equal because it thinks it's an equation. So I have to use a quote to start the whole thing. So now we have found 100, and we can stop. Is that okay? Any other questions? Yeah. 1? Okay. So this time we'll try to find 1. Or 0. Yep, they work out the same way. So we'll say we'll look for 1. So we always start from the middle, and we say 89 is greater than 1. But that means 89 is also going to greater than everything. 1 is also less than everything before 89. So we can now come to this particular conclusion. Nope, the other way. Sorry. Yep, it was the other way around. Okay, 89 is greater than 1. That means everything after is also going to be greater than 1. So we are ruling out 100, 101, and 120. And the next one that we want to look for is the middle of the remaining portion, which turns out to be 5. Okay, so we now compare 1 to 5. 5 is also greater than 1, which means we can also now rule out everything, including 5, and everything after that. So now these are all concluded to be greater than 1. And now we have only 1 left. And so we perform the last comparison. And we now conclude that 2 is also greater than 1. But that also means everything after that is also still greater than 1, which means none of them can be 1. And now we can conclude 1 is not in the array. So kind of the same way, if you think about it. Any questions about this? Yep.
The number of elements is even, odd. And 89 was middle of the array, okay? If it was even.
Okay. If it's even, then we can choose one of the 2 so-called middle ones. Yeah. So you can. You can choose one or the other. It will still work. Yep. But do we have a general idea of how the algorithm works? All right. So let's go ahead and try to write the algorithm to do it. I know you guys already can find the pseudocode to do it, but I want to kind of talk about how to derive the algorithm. So we'll just pretend that the pseudocode is not already in the text. How many people actually study before the class and know the actual algorithm already? Okay, we got a few. Okay, you don't have to know, because that's the idea is, how do we figure it out, by, working out a few examples. Okay, so I'm going to use this mouse pad, and I'll keep the spreadsheet behind just so that we can kind of refer back to it and go like, okay, what did we do again earlier, and so on. So the first question is always, do we have a sequence, do we have a conditional statement, or do we have a loop, as a general kind of thing? Yes?
Conditional statement.
We have a conditional statement. Now, but a conditional statement is a one-shot thing, which means we can only make a decision once. Now, we can have a nested conditional statement to make a few decisions in the process, but the number of decisions that you can make using even a nested conditional statement is fixed. It is a constant. Okay? Yep. We need a loop. Okay? I don't know whether it's a while loop or not. Okay? We'll just say it's a loop. Is that okay? Does it make sense that we need a loop instead of a single sequence or a conditional statement? Okay? All right, so we'll say that we need a loop. All right, so this is a loop, and whatever loop it is, whatever we do in between, I don't know yet, so I'm going to leave it empty. But because it is a loop, we kind of have to say when do we exit, when do we get out of the loop. This is a loop, but it is still a search algorithm. In other words, the same thing that applied to linear search still applies here. We stay in the loop only when we have not found what we're looking for, and we haven't searched through the entire array yet. Or if you want to look at the negation of that condition, that means we exit the loop only when one of two conditions happen. Okay, so we'll just go ahead and say one of these two, using an OR to join them. The first one is easy, okay? When the value is found. Okay, when the value is found in the array, we can get out. Does that make sense? Because I just need a confirmation of whether that value is in the array or not. So if I find it, then it's good to go. What about the second one? Well, I can't really say when the value is not found. Okay, because if I say the value is not found, am I referring to a portion of the array, or am I referring to the entire array? It is not clear. Yep? When we have searched through the entire array, or when we confirm that none of the elements can contain that value. How about that? So when we can conclusively make that conclusion. The nice thing about binary search is, remember, in 8 billion records, we only need 33 comparisons, right? So that means we are not comparing to every single element, because some comparison is very conclusive of, we can rule out 1/2 or 4 billion elements by one single comparison. So I would much rather say, how many elements can we confirm that do not have the value that we are looking for? Because one single comparison can confirm that many, many elements do not have that value. Okay? So we'll just go and change this statement to or when we can confirm none of the elements has the value. Okay. Is that okay so far? Well, we'll just say it. Yep. This is our first attempt of the algorithm, which doesn't even look like pseudocode. So what we realized after the first attempt is we kind of need some names, okay? Because without the names, what are we talking about? When we say the value or elements of what and so on. So we'll have some names. So we'll say array A is sorted, and we are trying to find the value K in array A. So now we're giving some names to the things that we refer to. The name of the array is A. Okay, the value that we are searching for is K. Okay, so we got some names, which is kind of handy. So now we can say when K is found in A. Okay, so we'll get rid of the when because it's double whened. So we'll say when K is found in A. And over here we can confirm none of the elements in A is K. Okay, there we go. So now we're starting to use variable names so that it is clear to what element, to whose element are we referring to, and what is the value that we are searching for. Everything needs to be named. So you do need to have your variables named. Yep, and then the outcome has to be named n. So that one you have to name it n. Yep.
I'm wondering if he's asking if we have to announce that like A is named.
No, you do not, because the homework assignment already describes that. The homework description itself describes that A is the array that is given to you, and the array, your algorithm is to find the longest run, and then the length of the longest run has to be stored in n as a variable. So I already know what those particular names mean. Yep.
So then, because I was asking, because I was going to use like v as variable instead of like 0, 1, 2, 3, 4, 5. Does that make sense? So then you could do like v plus 1 to like loop it to go through all of it. So would I have to put in there that v is the variable in the array, and then that the variable value is something else? Does that make sense?
So instead of B, he's using I, or instead of I, he's using B.
Yeah.
You can use any name for the other variables. So anything other than a and n, you can use any particular name if you want to.
But do I need to like let you know like that? So like, do I need to put that b is whatever, I is whatever?
You mean here to tell me what those variables are for?
Precondition?
No, you do not need to know. You do not need to tell me what the variables are for, because I can tell by your pseudocode.
Okay.
Yep. Yep. But in here it is important because I'm trying to derive the algorithm step by step from something that has no references to any name. So I need to I need to introduce those names as we go.
That makes sense.
Okay, cool. So now we look at this and go like, but how do we find k as a value? It's found in A. Well, we have to be comparing to a particular element. You cannot compare k to the entire array all at once. That doesn't work, okay? So k equals a does not work. You can only compare between k and a particular element of A. But how do we get to a particular element in A? Well, we need to use the array indexing operator, the square brackets, right? So that means we have to, now we can be more specific. Now we are basically saying, well, that means k equals to a bracket something, okay? But what is inside here, we don't really know, okay? All right, well, this is still progress because we know that we need to use array indexing, so that is progress. Yep.
In this instance, because we don't have a set, like a given number of elements in the array, is that something that we would have to find out or be given ahead of time?
When you trace, you need to know how long or how many elements are in the array. But when you are working on the pseudocode, then you use the bar notation to denote the actual length of the array, which we do not need yet at this point. Yep.
No, I have the same question.
Oh, okay.
How do we know how big the array is?
The bar notation. Bar tells us how many elements are in A. But we are not quite at the point where we can utilize the length of the array yet. Okay? All right, so when we look at this code here, okay, this is the latest revision of this code, then we go like, we got some question marks here. How do we deal with that question mark? So now we can go back to the sample that we had earlier, and we go like, so we compare this first, and then this is the next to compare, and this is the next to compare. So we have some kind of expression or some kind of variable to tell us the index of the element that we're comparing to. Okay, so how about we just call that, a particular thing here? We'll just call it variable m. So variable m, the only purpose of variable m is to tell us which element in the array should I be comparing to. Yep.
Two questions. So bar A bar minus 1, it kind of denotes the condition of being in an array pretty much, right?
A valid index is between 0 and bar A bar minus 1.
Right. Okay. So if you want to say that you're in an array, then you would just go less than or equal to or greater than bar A bar minus 1. So with this, when you have an m there, you're basically saying the same thing as the I, right? Or the B is the case
Which one?
So that A bracket, M bracket, that's the same thing as A bracket, M bracket, right? From the last assignment.
Well, the bracket notation is still the indexing operator, which means whatever is inside the square brackets is the index of the element, right? Because remember, huh?
You could have put an I.
I could have used I, but M makes more sense because midpoint. Yep. But if you want to use I at this point, that's fine too. Okay, so so we don't need to use a particular name. You can use whatever name you want. I'm just using M here. Okay, so are we still doing okay so far? With this code here. Yep.
With an unknown amount of elements in an array, how do we specify what M would be?
Oh, that's fine. We'll figure it out later. This is the whole idea of working on the algorithm step by step and just work out what we can at a particular point. Now, we know that we can only compare K to a specific element in A because that's how comparison works. So that means it's okay to make an assumption and say, well, we'll just say that variable M is controlling the index of the element that we're comparing to. But we are not worried at this point of how to compute the value of M to begin with. So we are working our way back. Is that okay? All right. All right. So going from here, what is the next step? So when we go back to the spreadsheet, what do you notice about how I choose M? First, it is this one. And then of the remaining elements that can contain the value, I find the midpoint again. Of the remaining elements that can contain the value, I find the midpoint again. So this is probably the most difficult part, or the part that is the biggest obstacle to figure out the algorithm in the case of binary search, is to figure out what else do we need to help us figure out M. We kind of know M starts from the middle, and then when it doesn't match, what are we doing? So, yep. We are changing M accordingly. Yep. Yep. And are we doing that in a repetitive fashion?
Yeah, so it'd be in a nested loop.
So be in the loop. Okay, very good. So that means in the loop, we are comparing K to M. Okay? If K is less than M, we do certain things. Else, if K is greater than M, A bracket M, we do something else. Okay, I'm going to use the nested loop approach here. So if K is greater than M, A bracket M, let me do this. And we have an AND if here and an AND if here. In other words, if K and A bracket M are the same, there's no special action to do. Because if K does equal to A bracket M, we would have exited the loop because of this. So we don't have anything special in the loop to deal with that case. So we want to look at this one and go like, what does it mean when K is less than M? So we go back to the spreadsheet, because the spreadsheet can tell us what happens when that is the case, when K is less than A bracket M. This is a very good example of what happens when K, which is 1 in this case, is less than the element that we're comparing to. So the conclusion of that comparison is not only is that particular element, A bracket M, is ruled out, but everything after that is also ruled out. Right? So we'll write it in the pseudocode, at least to note it. Okay? So I'm going to use // here to basically say this is just comments. It is not the actual code, but it's an observation that might prove to be useful later on. So now we can say A bracket M plus 1, A bracket M plus 2, all the way to A bracket bar A bar minus 1 are ruled out. Does it make sense? Because the array is assumed to be sorted in a non-decreasing fashion. So if A bracket M is already greater than the value that I'm searching for, then everything after that in the array cannot be the value that I'm searching for. So we can just rule them out. Is that okay? So we can now apply a very similar reasoning here and say that if k is already greater than a bracket m, then a bracket m minus 1, a bracket m minus 2, dot, 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 to the first one, which is a bracket 0, are now ruled out. Now, I have to be very clear that a bracket m itself is also ruled out. Okay, so I'm going to add a bracket m back here. Is that okay? Yep.
I just want to make sure. A bracket or bar minus 1,
Uh-huh.
at the very last element?
It is the index of the last element. And that has to do with we start counting from 0. So if you think about like a very short array where you only have 2 elements, if the first element has an index of 0, then the last element is going to have the index of 1. That turns out to be bar a bar, which is 2 minus 1.
Okay.
All right, so we'll say, well, that seems to be a pretty useful insight of what we saw in those examples. And we call this another version of the algorithm. So the next one is going to go like, well, just having a observation of a bracket m plus 1, and everything after that can be ruled out is good. But how is that changing m itself? Because the bottom line is we need to move m, right? So now the question is, well, how do we keep track of m in this case? How do we compute m? That becomes the question. Now, these examples, let me show one that is relevant. Okay, this is a good one. Now, this is a good one because the way we rule out the possible values is not lopsided. We are not basically saying everything after this is ruled out. This one is kind of like we rule out some after, and then we rule out some before. So somehow we have to keep track of the range of indexes that may still contain the value that we are looking for. Because it's not really just everything after or everything before. It is a specific range that has a beginning and an end. Is that okay? So this is the part that where that may not be easy to come up, is to figure out that we need to keep track of a range. Yep.
Do we need to create another variable?
Yep, 2 variables indeed. So now we need to create 2 variables. We need to create a variable b, or however you want to name that. B is the index of the first element that may be k, and then E is the index of the last element that may be k. In other words, we're keeping track of a range of indexes in array A, such that if an index is within that range, there is still hope that the value k is within that range. Are we doing okay so far with that idea? Okay. Well, if that is the case, let's go back to the trace here and figure out how B and E would change over time. Is that okay? Well, the way we can denote that is to say which elements may still contain the value. So we'll go ahead and insert one column to the left, because initially, before the first comparison, the entire array can contain that value. So I'm just going to use a highlight color to indicate that. Is that okay? This is before the first comparison. The entire array may contain that value. After the first comparison, we have ruled out the last 4 elements, which means the first 3 elements may still contain the value that we are looking for. After the second comparison, we rule out the second element and the first element, and we rule out the last 4 elements, which means this particular element may still be the value that we are looking for. It takes one more comparison to confirm that, oops, that is not what we are looking for, and now we have nothing left. So when there's nothing left, then we conclude that, well, that value is not in the array. Is that okay? So the yellow part is keeping track of what part of the array may contain the value that we are looking for. This is in the first iteration or before the first iteration, after the first iteration, after the second iteration, and this is going to be the result of the third iteration. Well, let's look at the other examples. In the second example, before the first iteration, before the first comparison, we go like, well, anything in the array may contain 3, okay? After the first comparison, we rule out these 4, which means the first 3 may still contain the value 3. Of the 3 remaining, we pick the one that is in the middle, we compare and go like, that is not what we're looking for. In fact, it is greater than. So now we can rule out the second and all the rest of the array. So we are only left with the first element that may contain the value that we're looking for. And that becomes its own middle index or middle element. We do the last comparison, and now we conclude that nothing in the array has the element that we're looking for, has the value that we're looking for. Is that okay? So we basically want to keep track of the yellow part. And you can see how in some cases the yellow part is not just from the beginning to the end, or the way we narrow it down is not in one single direction. We approach it in both directions. With this one, same thing. Initially, we think any one of the 7 can be the value that we're looking for. After the first comparison, we are only left with the last 3 elements that may contain the value that we're looking for. But in this case, we're lucky. The middle part of the last 3 elements is the value that we're looking for, so we can stop. Is that okay? So I should probably highlight this with yellow too, because that is actually the value that we're looking for. Yep?
So are we using B and E as a way to assign elements or like index elements in the array? Like B would be the A bracket, 0 bracket.
Yep.
And E would be changing.
Yep. Yep, exactly. So, yep, go ahead.
Then B and E change according to where that range changes.
That is correct. B is always marking the beginning of the range. E is always marking the end of the range. So that means, in the second column, B is here and E is here. And then in the next column, both B and E are here because the beginning and the end of range is the same number. That range only has one single number, which makes you kind of question, what about how do we represent when there's nothing left? Well, do you observe that B is always less than or equal to E? When there is something to look for? What do you think happens when B is greater than E? That means there's nothing left. Because B is supposed to be the beginning of the range, and E is supposed to be the end of the range. If the beginning is greater than the end, that means there's nothing in between that we need to look at.
If B and E equal, then that means that you would have found the value?
Nope. That means we have one element left that may contain the value. Is that okay? Okay, so if I want to make it even more clear, instead of saying B is the index of the first element that may be K, so the other way to say this that is probably more precise is any element A bracket I that may equal K has I being greater than or equal to B. And then same thing here, any element A bracket I that may equal K has I less than or equal to E. Is that okay? That kind of defines the range that we are looking at. So if this is how we define B and E, which means B is the lower bound of the index and E is the upper bound of the index, what happens when B is greater than E? There's no such I that can satisfy this requirement anymore. Because no I can be greater than or equal to B, but B itself is greater than E, and still have I being less than or equal to E. That cannot happen. Is that okay? So when you go back to the picture, okay, and this is probably the best way to represent it. is we just need to keep track of what is B and what is E. After each comparison, we just have to move E in this case. In this case, we move B. So depending on whether K is greater than or less than the array element that you're comparing to, we have to adjust one of the two. Is that making any sense? Okay. So we'll see. Yep.
So in this case, because there's only an odd number of indexes, this thing, when B equals to E, you know you're closing to the end of the sort. Whereas I'm guessing in the even number of indexes, it has to be B plus 1 equals to E.
No, it will still work out. I'll show you an example later on where we are going to deal with an even number of elements. It's not a problem. Okay, so we'll copy and paste this because we made some progress here. Copy and paste. So now we go back and say, well, we kind of know what to do now. We know what to do when K is less than A bracket M. So what do we need to, which end do we move when K is less than A bracket M? Do we move the end up or do we move the beginning down? We move the end up because everything after M is excluded. And so we have to move the end of the range up. So in this case, we say E equals to something related to M. Okay? So now the question is it just M or is it M minus 1? It's M minus 1. Why is it M minus 1? Exactly, because it is inclusive. The range is inclusive. So if I do not make it M minus 1 and instead just M, that is still suggesting that A bracket M can have the value that we're looking for, which is not possible because we already confirmed directly by the comparison that A bracket M is not what we're looking for. So that's why we have to move it up one past the index that we were just using to compare. Okay? So that means in the other one, we have to go in the opposite direction. So in this case, we have to move in the opposite direction and change the beginning of the range so that it is M plus 1. Is that making any sense?
So as far as like the cells go, like M is what we compare, M minus 1 if there's less would be compared to this range to be.
We are not moving the cells, we're just moving the range. In other words, imagine that you have two bookmarks in the book. And the pages between the two bookmarks are the ones that you might want to read. Okay? So what you do is you're looking at the two bookmarks, you find the bookmark, you find the page that is right between the two bookmarks. You do a comparison, and then based on that comparison, you move one of the two bookmarks, but you have to move it past the page that you're looking at so that the remaining pages of where the new bookmark positions would include the range that whatever you're looking for can still be at. Okay? All right. Well, we call this another revision because this is a major change. And I would say with the binary search algorithm, this is the trickiest part, is to figure out that you have a range to deal with. And I cannot explain how mechanically you can figure out that, oh, we have to maintain a range, and the range can be maintained by a beginning and an end. So that is kind of like, that's the magical part of this algorithm. Okay? Because once we know the range, we actually know the answer to this question already. How can we confirm that none of the elements in array A has K? What do you think? We just talked about it a little bit. When B is greater than E, very good. So when B is greater than E, then there's no index that can satisfy the requirement of being greater than or equal to B and at the same time less than or equal to E. Okay? So that's great. We are only missing a few really, really small parts now. Okay? The small part is, well, we know how to move E, B, and E, but once we move B and E, let me go back here. Once we move the B and the E, how do we know this is the next M? When B and E initially are here and here, how do we know that M is here? That is the question. What do you see is kind of giving that away, the calculation here? Okay, you got some of the major components.
E minus B should be integer.
The average, which means you just add those two numbers and divide it by 2. Now, it works even when you're dealing with some insane, crazy index, okay? So let's look at this one here, okay? This is B, oops, and this is E initially, and then this is E, and this is B. This is B and E at the same time. Where's our M? Well, the M is here. So you look at the M, which is 17. Isn't that 14 plus 20, which is 34, divided by 2? Yep, works out. What about here? The beginning is here, the end is here, and this is the middle one. Okay? 15 is 14 plus 16 divided by 2. Cool. What about here? 14 plus 14 is 28. 28 divided by 2 is 14. That dictates the last comparison, or where we're comparing to. Oh, okay. So in the algorithm, we can now say, we now know how to determine M. Okay? And so now the question is, do we determine M at the beginning of an iteration, or do we determine M at the end of an iteration? So that's the question, because we know M has to be determined at some point, and it has to be iterative. It is not something that we do just one time before the loop, or something that we do one time after the loop. This is something that we have to do per iteration. Yes?
Wouldn't it be before so that we know what to compare to K?
Yep, exactly. So it has to be done before, because we have to determine M before we use it as an index. So we have to do it here. So at this point, I'm just going to give you the code that works only in this example, okay? Because we haven't, the initial number of elements, or the number of elements in the array is 2 to the power of something minus 1, okay? Because it's 7. If the number of elements is 15, it will always work. If it's 31, it will always work. If it's 63, it will always work. Okay? So we'll deal with that problem later. You can see how procrastination is really the best way to start programming. Because if you do not procrastinate and you try to figure out every single detail all at the same time, then you have way too much detail to look at all at the same time. But doing it this way means you're looking at a few major things at one time, and then you work out other things a little bit later. All right, we're almost there. What is left is, well, what about the initial values? Yeah, go ahead.
We need to assign B and E elements to them.
Yep, and where do we want to do the initialization? Before the loop, in the loop, or after the loop? Before the loop, very good. Okay, so initialization refer to things that we do before the loop. So we have to initialize B with something, and E to be initialized to something. B is the index of the first element that can contain the value V before the first comparison. Well, everything can have the value, so the first index is going to be 0. And what about this one? The index of the last element before the first comparison that may contain the value K. Bar A bar minus 1, because that's the index of the last element. So are we good so far? All right, so now we got one last question left, which is, what kind of loop are we dealing with? Are we dealing with a repeat until loop, which is a post-checking loop, or are we dealing with a while loop, which is a pre-checking loop? So you have to look at the condition. The condition is right here, and you have to ask the question, well, before I perform the first iteration, do I have any useful value for the condition to evaluate? The answer is no, because M is not determined. M is only determined, or is only computed in the loop, in the iteration itself. So we cannot perform, we cannot evaluate this condition unless we have gone through at least one iteration. So this is one of the 5% of cases where you have to use a repeat until loop, because you have to perform at least one iteration in order for the exit condition to be meaningful. And this is, once again, one of the rare cases. The more common cases is to use a pre-checking loop. But in this case, a post-checking loop makes more sense, a lot more sense. And there you go. This is the binary search algorithm. And if you want to get rid of some of the clutter, we can get rid of the comments. The comments, in a way, is really helpful because it explains why we do what we do in the conditional statement. But if you just want to look at the code itself, this is what the code looks like. Do we have any questions? Yep.
So the n equals b plus e divided by 2 on an odd, on an even number of lines.
Mm-hmm.
1, 2, 3, 4, 5, on an odd number of lines.
Mm-hmm.
But how does it divide
It's
an
not.
even number of lines?
Okay. Well, let's address two questions, okay? The first question is my claim that if bar a bar is a power of 2 minus 1, then we will never have to worry about the case where b plus e divided by 2 is not a whole number.
Well, if you can't pick the middle of 6 numbers.
Wait. Let's address one problem at a time. Okay? So the first question is, why do you think that when bar a bar, okay, the number of elements in the array, is a power of 2 minus 1, okay, which means it is 1, 3, 7, 15, 31, 63, and so on. If it's one of those numbers, then we really don't have to worry about b plus e divided by 2 is not a whole number. Why is that?
You always split it into 2 with exactly one number separating the top and the bottom half across multiple levels, cascading levels.
Yep. And can we prove that? So now the question is, if I start with a power of 2 minus 1, okay, and I pull one card out of the stack, remove 1/2 of it, what is remaining, can we also claim that that is going to be a power of 2 minus 1? Okay, let me make it clear. Okay, so this is the, if you want to know what is computer science, this is computer science. It is the reasoning, the math behind the whole thing that makes it computer science. Programming is not computer science. And that's why programmers do not get paid the same as computer scientists. Who asked that question? Because you asked that question because you have not looked up the Bureau of Labor Statistics website. I'll look it up later. Okay, so we'll look it up, and then you guys can decide for yourself which occupation you want to get into of all these choices. So we are looking at cisp300. Where is it? There you go. And okay, so now the question is, if I start with 2 to the power of n minus 1, okay, n can be any positive integer, and I say, if I take this number and subtract 1 from it, and then we divide whatever is, let's say take 1 divided by 2, does that equal to 2 to the power of n minus 1, the whole thing subtract 1? That's what I'm asking. It seems to make sense, okay? If you look at look at 63, okay? So we look at 63, we say, okay, 63 itself, is 63 a power of 2 minus 1? What is n in that case? N is 6. 2 to the power of 6 is 64. 64 minus 1 is 63. So 63 does fit the requirement of being a power of 2 minus 1. Is that okay? So I take 63, I subtract 1 from 63, and then I divide it by 2. So 63 minus 1 is 62. 62 divided by 2 is 31. So now the question is 31 2 to the power of 5 minus 1? Okay, so we take 31, and then we do the same thing. 31 minus 1, the whole thing divided by 2. Is that, 2 to the power of 4 minus 1 this time? It does. So how do we prove it? Okay, so let me backtrack a little bit and say, can we prove this using algebra? And somebody's going to complain, but this class has no prerequisite of algebra. Well, if you don't know algebra, the chances of you becoming a successful programmer is going to be limited. Okay? I just have to be honest. Because guess what programs mostly have? Comparisons, expressions, equations, and stuff like that. And in order to understand somebody's program, you need a good handle on algebra. Now, calculus, I have questions about whether you really need to know calculus to become a computer scientist, but algebra is a must. Okay, so we look at this and go like, well, can we prove it? How do we prove it? Well, you always want to make the two sides look about the same, so we can say, well, what if we multiply 2 to both sides? Okay, if you multiply 2 to both sides, then you get this much left on the left-hand side, and then the other side becomes, well, not too exciting, just that, right? Then you say, but I can distribute. So when you distribute, it becomes 2 times 2 power to the power of n minus 1, and then the whole thing minus 2, right? And then you go like, oh, wait, I recognize this. 2 times 2 to the power of 2, n minus 1 is 2 to the power of n. So that becomes that, right? Then you go like, we can move that minus 1 to the other side. In other words, I can add 1 to both sides. If I add 1 to both sides, then the left-hand side becomes 2 to the power of n minus 1, and then the other side becomes 2 to the power of n minus 2 plus 1. Wait, negative 2 plus 1 is just minus 1 or negative 1. Done and approved. And that's algebra. Yep.
We can do the easy one. This is the left one, left side. Numerator, we have negative 1 minus 1. We get minus negative 2.
Yep.
And by factoring 2,
You can do that too. Yep. You can basically move this minus 2 into here, and then cancel that out to 1, cancel this one to minus 1. Yep, that works too. It's algebra. But sometimes the scenic route is fun. Unless the math professor is asking for the optimal proof, any way that you can establish the equality is going to work. Yep.
So what's the behavior of the processor when it looks in element 0? Oh, wait a second. Maybe I missed it. So if there's 6 elements and it has to pick the middle of it, does it go to the 3rd element or the 4th element?
It's up to you. You can choose one or the other. Doesn't really matter. So getting back to our code here, and some people may think, well, what if b plus e is an odd number? Then the odd number divided by 2 is going to be something 0.5, and we don't have an index, that is something 0.5. Well, we can always just force it to become an integer by taking the floor of that. So the next question is, but what is floor? Well, it's in the notes. It's actually defined in the module, but if you want to, want me to explain it quickly, this is how I can explain what a floor is. So the floor of x is the largest integer that is less than or equal to x. That's it. Okay, so Let's do some exercise. What is the floor of 2.7? It is the largest integer that is less than or equal to 2.7, which makes it 2. The floor of 1.2 is 1. The floor of negative 2.2 is negative, negative, negative 3. It is the largest integer that is less than or equal to negative 2.2. Negative 3 is the largest integer that is less than or equal to negative 2.2. It is not the same as rounding. But since an index cannot go negative, that is not an issue. Is that okay? All right. So you can use a floor, okay? That works. But you can also use a ceiling. I mean, think about it. If a function is called floor, don't you think there has to be a function called ceiling? So what is the ceiling of x? Well, it's just basically the reverse. It is the smallest integer that is greater than or equal to x. Okay? So what is the ceiling of 2.7? 3, yep. What is the ceiling of 1? 1 itself, yep. What is the ceiling of 0.5? It is 1. No, it's 1. What is the ceiling of negative 0.5? No, it's 0. Because it's the largest integer that is greater than or equal to. Okay. All right. Yep, you can use ceiling instead of floor. That works too. You can sometimes use ceiling and other times use floor. That will still work. And you don't even have to be consistent. You can flip a coin and say, for this iteration, do I want to use floor or ceiling? That will still work.
So the floor and the ceiling is how the computer resolves the n equals b plus c divided by 2 when it gives.
Well, how it chooses one or the other. Yeah.
So if it gives a 2.5, then it picks a floor or a ceiling.
Then the floor will be 2. The ceiling will be 3.
And it'll pick one of those?
No. Depending on whether you use floor, if you use floor, it always picks 2 in that case. If you use ceiling, it will always pick 3.
So do you add that in your code or something, or is that just?
It's all in the module has the finished code, which uses floor. Because floor is automatic. In C and C++, when you divide an integer by another integer, the result is automatically truncated, which means it is using the floor of the value.
So your program will pick which one it wants to use.
Well, the program is just, it doesn't take any work to compute the floor. And that's why we use the floor. Yep. All right. Are there any further questions about this algorithm? The binary search algorithm. No questions? I know it's kind of late to take a break, but we'll go ahead and take a 5-minute break anyway. So right now it's 7:14, so we'll be back at 7:19. All right. Well, I'm going to restart the lecture. The audio is back up and the recorder is still on, so we are good to go. All right. So I'm going to go write the code first. Okay, are you guys ready? So we'll initialize B and E, and then we have the repeat until loop. So in the repeat until loop, we first figure out what is M. M is the floor of B plus E, the whole thing divided, oops, okay, B plus E, the whole thing divided by 2. There we go. And then we do a comparison. We compare K, which is the value that we are searching for. And we first check for less than. It doesn't really matter which one you check first, okay? And if that is the case, if K is less than, that means we can rule out A bracket M and everything that is after that. So we move the end to be M minus 1. Otherwise, we try to confirm the other way. Is K greater than A bracket M? If that is the case, we update the beginning because we are moving the beginning of the range down to M plus 1. And then we have and if, and that's the end of this, the body of the loop. Then we say until we confirm that A bracket M equals to K. That means we have found it. Or we confirm that B is greater than E, which means there's nothing left in the array that may contain the value K. I intentionally did this without indentation, just so that it becomes very difficult for you guys to read and see what is embedded into what else. Because now I can say, well, let's see whether indentation has value. Yep.
I just had a question. Why are we using an if statement inside the if statement and not just using
Else if?
else? Yeah.
So there are two actual else ifs. Some programming languages support an actual else if, which means you're having a second branch to a conditional statement, but C does not. So when you say else if in C, it actually means this. The else starts a statement, and it just so happens that the statement inside the else is an if statement. So they're actually nested in terms of syntax, even though a lot of people show else if on the same line as if it is a flat structure, but it's actually nested. All right. Well, okay, so let's do some indentation. Indentation in a spreadsheet turns out to be very easy. You just have to mark everything that you have to indent, and then you look for the indentation tool, which is usually, because I have a small screen that doesn't fit the entire toolbar, so I have to look for it here. So this, along with, oops, okay, this and control click, 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 also needs to be indented because these are inside the high-level conditional statement. So we have to indent these one level. And then this by itself also has to be indented one last time because that is the most deeply nested statement of the entire structure. So now it looks a little bit better because now we know that line 9 is a nested statement of line 8 to 10, which then becomes a nested statement within line 5 to 11, which is by itself a component of the loop that starts from line 3 and it ends on line 12. Okay, so indentation is for your benefit because as a programmer, as a human, without indentation, it is very difficult to find, oh, I'm at the end of a branch, but where am I supposed to go next? Okay, but now it is a lot clearer. Is that okay? All right, so we are ready to trace, and we'll go ahead and open a new window for tracing. So we'll park the new window next to the other one and give it a new tab. And we have line number. We have comments because we got conditions to evaluate. And we got a whole bunch of stuff to track this time because we got B, E, M. Those control the indexes. We have K, which is the value that we are searching for. And I'm going to shrink some columns as we speak, because otherwise I will run out of horizontal space pretty quickly. And then now we have space to put the actual array. So we have array A. How many elements do you want to use in this particular array? You can try some tricky numbers like even numbers. 8. Let me see if I have room to fit 8. Okay, I might. So we got bracket 0, bracket 1, bracket 2, bracket 3. And by the way, there's a programmatic way to generate these bracket stuff using spreadsheet equations. Okay. And then we'll take all of these and make them smaller. Okay, that might work. But when we refer to A, we are actually referring to column G to column N. So that's why I tend to group these together to be just A. So when we refer to A, we are referring to all 8 columns. When we refer to A bracket 1, then we're referring to just column H. Okay? So it's a concept thing. I just want to make sure that the notation matches the concept. There we go. And we probably want to do some precondition here.
Question.
Yep.
If we do trace an array for you in our homework, do we need to set it up like that
Yes.
with the bar all the way across?
No, that part is not needed. So you don't need to do this part, but you do need 1 column per element in the array. Yep. All right, so we'll go ahead and start with an array that is sorted. It doesn't really matter how it is sorted. So okay, there we go. And you guys can tell me what you want to search for. It doesn't even have to be integer. You can look for like 6.5 if you want to. So what do you guys want to search for? 3. Okay, we got 3. 6.5. Okay. 16. Okay. So we'll try to do all of those. Okay. So I'll just kind of write it down on the whiteboard. Okay. Don't have a pen. Okay. I got my tablet, so I can write it here. So we got 3, 6.5, and what? 16. Okay. So we'll work on 3 first. Okay. So here's 3. That's the precondition. So I need to show both the source code and the trace at the same time. In the source code, I'm using the row number as the line number, because otherwise I just have 1 duplicate column doing nothing. So we'll just use the row number as if it is the line number. So now we start with line 1. B is initialized to 0. Line 2, E is initialized to 7 because it is 8 minus 1. And then we get to line 4. We do not trace line 3. Line 4 is initializing M to a value of 0 plus 7 divided by 2, which is 3.5. But then we take the floor of that, which means we only have 3. And then we go to line 5. We evaluate the condition. K is 3 is less than A bracket M, which is A bracket 3, which has a value of 6. So 3 is less than 6 is true. Right? Because we are looking for, because K is 3, A bracket M is A bracket 3, which is 6. 3 is less than 6 is true. Okay. That means we go to line 6, which is the then branch of the outer conditional statement. It changes E, so E is now 3 minus 1, which is 2. And then we get out of the conditional statement, because after line 6, we get out of the outer conditional statement, which goes to the end if on line 11. But we don't track line 11 because it doesn't really do anything. So the next line to track is on line 12, which is the until line. The until line has a longer condition to track, so we have to now say, what is A bracket M equals to K? That is false. In the case of a disjunction or, if the left-hand side is false, then you have to evaluate the right-hand side, because if the right-hand side is true, then the whole thing is still true. So now you have to evaluate the right-hand side, which is B is greater than E, which is also false. False or false is false. So that means we have not satisfied the exit condition yet. So that means where do we go next? Back to line 4. Thank you. Because we are not done with the loop. So we go back to line 4, and then we have to recompute what is m. This time it is 0 plus 2 divided by 2, which is just 1. And then we re-evaluate the conditions. On line 5, we evaluate is k less than a bracket m. K is 3, m is 1, a bracket m is 2. 3 is less than 2 is false. That means we have to go to which line again? We have to go to line 8, exactly, because if the condition of the outer conditional statement is false, then we have to go to the else branch of the outer conditional statement, which is a conditional statement itself, and that's why we end up on line 8. On line 8, we have to answer the other question, which is k greater than a bracket m? Oops, typo. K is greater than a bracket m. The answer is true, because k is 3, m is 1, so a bracket m is a bracket 1, which has a value of 2. 3 is greater than 2 is true. So now we update b on line 9. B is m plus 1. So now, okay, let me change the header so that we can at least see the column header like that. It's good to be able to see the array values as well. Okay. So here we're on line 9. Line 9 is supposed to update b, which is m plus 1. M plus 1 is 2, okay? And then we go to the until on line 12. A bracket m equals k is false, because we just know that it's greater than, k is greater than a bracket m. B is greater than e is also false, because b and e are the same. They're both 2 at this point. So now we again has false or false, which is false. Then we go back to line 4 again. This time m is pretty easy to compute. 2 plus 2 is 4. 4 divided by 2 is 2. Okay. And then we go to line 5. We compare k to a bracket m. K is 3. A bracket m is a bracket 2, which is 5. 3 is less than 5 is true. Then we go to line 6. Line 6 is updating e. E is now 2 plus 1. Oops, 2 minus 1. Okay, it's m minus 1. M is 2, so e is now 1. And then we get out of the conditional statement. We get to line 12. And this time, a bracket m equals k is false, but b is greater than e is true. So the disjunction is true, and we're done. Okay? Are we good so far? Okay. So now I'm going to copy the first part of it. Actually, I'm going to copy all the columns, because this preserves the width of the columns. So I copy the whole thing and paste it here. Except we have to kind of get rid of this portion here. The other portion we can kind of keep, because they are the same. The initialization is the same. All right, so the next value is 6.5. So k has now a value of 6.5. And I'm just skipping to line 5 here, because the first 3 lines will execute exactly the same way as the last time. K is less than a bracket m is, k is 6.5, a bracket m is a bracket 3, which is 6. 6.5 is less than 6 is false. Thank you. So we go to the else, which turns out to be the beginning of a nested conditional statement. Then we ask, is k greater than the value? The answer is true. So now we execute line 9. And line 9 updates B. So it is now m plus 1, which is a 4. Then we go to line 12. A bracket m equals k is false. B is greater than E is also false. So the whole thing is false. Forces us back to the beginning of the loop on line 4. On line 4 this time we have 4 plus 7, which is 11. 11 divided by 2 is 5.5. The floor of 5.5 is 5. So m is now getting a value of 5 this time. Go to line 5. And then we compare k is less than a bracket m. K is 6.5. M is 5. A bracket 5 is 10. 6.5 is less than 10 is true. Then we go to line 6. We update m to be, we update E, sorry, I misspoke. And once again, it's really helpful to break this up so we can refer to the value of k as well as a and look at and keep track of all the column headers at the same time. So scroll back down. On line 6, we are updating E. E is m minus 1. M is 5. 5 minus 1 is 4. So E now has a value of 4. We then continue on to line 12. A bracket m equals k is false because we have just shown that they do not equal. B and E are the same, which means B is greater than E is also false. False or false is false. Then we go back to line 4. 4 plus 4 is 8. 8 divided by 2 is 4. So now m is 4. Go to line 5. A bracket m, k is less than a bracket m. K is 6.5. M is 4. A bracket m is a bracket 4, which is 8. 6.5 is less than 8 is true. We go to line 6. Line 6 updates E. E is now 4 minus 1, which is 3. Then we go to line 12. A bracket m equals k is false because we just already know that one is greater than the other one. But B is greater than E is true, which means the entire thing is true. And now we exit the loop and done. We're done. Is that okay? Are you guys getting bored? No. That means I'm not doing my job right. Because at this point, I was hoping someone to say, this is so boring. This is the same thing over and over again. Because it is the same thing over and over again. Okay? All right, so one last one, because I did promise that we'll trace all three values, 3, 6.5, and 16. So let's figure out what is going to happen when k is 16. Okay, paste. And once again, I'm going to cheat a little bit here and keep some of the traces because it's still applicable. And we'll start with line 5.
So, quick question.
Yep.
Line 2 says that E gets bar A bar minus 1. So, do we have to just pick the amount of elements that we want, and then that drops into, so there's 8 there, and then we just drop that into line 2 as the value of E?
No, but you're almost right. Bar A bar is 8, but 8 minus 1 is 7.
If we didn't write the algorithm that initializes the array, if we just write A bracket 0, bracket 1, bracket 2, bracket 3, all the way to 7, then we just initialize E as 7 then?
Well, by doing this, it is implied that the array has 8 elements, which is bar A bar. So that's why when we calculate bar A bar minus 1, it is 8 minus 1.
Right. So if we were to write code tracing that looked like that, then
Right.
we have to put the elements and then initialize E as 7, right?
Say that one more time.
I don't want to try to confuse you. I apologize for not being.
No, I'm just clarifying what you're saying.
piece of code that we wrote,
Mm-hmm.
we didn't have to write the value of B is bar A bar minus 1, right? So
It still need to rely on bar A bar because we need to terminate the loop at some point. And the terminating of the loop still depends on the number of elements in the array.
okay.
So bar A bar appeared inside the condition of the while, but not outside of the condition.
I see why we had to include E, but what if there was an infinite amount of elements?
If you have an infinite amount of elements, you cannot actually compute the midpoint anymore. So the algorithm cannot handle an array that has an infinite number of elements. You have to know the number of elements in the array before you get into the loop.
Okay, so you always will have to figure out the amount of elements in your array.
Correct. Yep.
Hypothetically, if we were getting homework and we had to trace this algorithm,
Uh-huh.
would we be given the amount of elements in the array?
Yes.
beforehand?
Yep. Or there will be instruction of what you can assume, or whether you can come up with your own array. Okay. All right, so getting back to here, this time we are changing k to 16. And this time I'm going to separate the panes earlier because we have to do it anyway later on. Might as well do it now. All right, so now we perform the comparison. K is 16. 16 is less than A bracket M, which is A bracket 3, is false because K is actually larger than every single value in the array. So this is now false. We go to line 6. We change E, which is the end. Wait. Okay, I got it wrong. K is 16. 16 is less than A bracket M is false. Then we update E.
We would go to the else nested if statement.
Oh, right, because it's else, we go to else. Sorry. Okay. Brain fart. Happens. Okay, so on line 8, because the condition is false, we go to the else. Okay. So when we go to the else, we check whether K is greater than A bracket M, and that is true. So that means we go to line 9. Line 9 is updating B, and B is M plus 1, so that is 4 in this case. We go to line 12. A bracket M equals K is false. And right now B is greater than E is also false. False or false is false. So that means we go back to line 4, recompute what M is. So in this case, B is 4, E is 7. 4 plus 7 is 11. 11 divided by 2 is 5.5. The floor of 5.5 is just 5. We go to line 5. We perform the first comparison. K is less than A bracket M is false. Then we go to the else. And then on line 8, we perform the other comparison. K is greater than A bracket M is true. Then we go to line 9. We adjust B again. So this time it is it's 5 plus 1, which is 6. Correct. And then we continue on to line 12. A bracket M equals K is false. B is greater than E is also false because E is 7. So 6 is greater than 7 is false. Then we go to line 4 again. Okay. 6 plus 7 is 13. 13 divided by 2 is 6.5. 6.5, the floor of 6.5 is just 6. So M is now 6. We go to line 5. We ask, is K less than A bracket M? The answer is false. We go to the else, and then we ask a second question. On line 8, is K greater than A bracket M? The answer is true. We go to line 9 again. Line 9 is going to update B again. This time it becomes 7 because it is M plus 1. We go to line 12. Line 12 has basically the same answer. A bracket M equals K is false. B and E are now the same, which means B is greater than E is still false. False or false is false. So we go back to line 4. And then we say, what is 7 plus 7, the whole thing divided by 2? That's just 7. So now we look at 7. Then we go to line 5. These conditions are remaining the same because 16 is larger than any value in the array. So 16 is less than anything in the array is going to be false. On line 8, k is greater than is always going to be true because we picked a value of k that is greater than everything in the array. So we go to line 9 again. This time we update b to be 7 plus 1, which is 8. We go to line 12. And this time a bracket m equals k is false, but b is greater than e is true. So the whole thing is true. We exit the loop, and we're done.
Line 1 should be
Huh?
8. We write down 1, but it should be 8.
Oh, okay, should be 8. There we go. Thank you. So are there any questions about the trace? Is it boring? Coming up with the algorithm is the tricky part. That's the part that is really, really hard to teach. And it gets harder to teach if we don't know the tools really well. So if we really have to know the tools, which are the loops, the conditional statement, the conditions, the comparisons. So we have to have all of those tools first before we can actually come up with the algorithms. Algorithm design is not easy, because it is a synthesis process. It's not mechanical. And that's why it's kind of difficult to teach that. I can kind of explain what goes on in my mind when I try to come up with an algorithm, but only to a certain extent, because there's a certain portion of thinking or processing in a head that is not explicit. So I cannot convey that part that is not explicit. Yep.
See that in this algorithm, we just compared all of these elements, but we don't know if we found or not.
Oh, okay. So if you want to come to a conclusion of whether we found the element or not, then you can over here. So I'll give you a template, and you guys can help me fill in the blanks. Okay. So when can we confirm k is in A, and when can we confirm that k is not in A? Oops. That's right. So when you look at the exit condition, there are only two reasons we can use to get out of the loop. Either a bracket m does equal to k, which confirms that, yep, we found it, or b is greater than e, which means no element in the array matches the value of k. So after you get out of the loop, when you need to make a conclusion or decide what to do one way or another, you just have to confirm whether a bracket m equals k or not. Because if a bracket m does equal k after the loop, then we confirm that we have found it. If not, that means the other condition got us out of the loop, which also means k is not in A. So that's basically how we can make a conclusion. Yep. Yep.
So the or condition for the repeat until is for the b is greater than e is just us checking to make sure that we've gone through all of the elements in the array. It doesn't have
That is correct. Yep.
There's no factor in whether or not k is actually in the array.
So when b is greater than e, that means there is no index left that to represent elements that can still have the value k.
So that's unless we actually find the value, that is the actual reason why we're stopping.
Yep. Mm-hmm. But if you think about it, what is happening is, from your perspective, b is always moving in this direction, and then e is always moving in that direction. So the range of indexes of elements that can still be containing k is smaller and smaller, because every single time you have a comparison, they get closer and closer together until they overlap. And when they do overlap, that means you have no indexes left. And that's why we can conclude that there's no element in A that has the value of k. Is that okay? Oh, cool. All right. So this is binary search, which is a very useful algorithm, because any type of array that is sorted can use binary search. It's a very fast algorithm because it's always the number of times you have to search is basically the log of the number of items in the array. So that means the number of comparisons grows very slowly compared to the size of the array. Now we illustrated that in like the previous class. When population doubles from 8 billion to 16 billion, you only have to add one comparison. So in 34 comparisons, you can confirm whether something is in the array or not. And that array has 16 billion entries. That is a very fast search algorithm. But it does rely on the array being sorted to begin with. So that means, sorting algorithms are also very important, because how do you keep an array sorted? You need a sorting algorithm to do it. So are we good so far with this stuff? Okay. So getting back to the browser, we are now done with searching in a sorted array. So that part is done, and we are now moving on to invoking and returning from a subroutine. So as I said earlier in the class today, this is kind of like a brand new topic. It is not disconnected from everything else that we have talked about, but it is a concept that is kind of orthogonal, which means, this one, it is not about control structure. It is not a conditional statement. It is not loops. And yet it is not about arrays. This is about being able to write subroutines and make use of subroutines. So subroutines are important because they help us organize big and complex programs. Okay? Who wants to read a subroutine that is like 500 lines long? No one. And why don't you want to read a subroutine that's 500 lines long? Well, what makes it difficult? If you think about it, what makes a subroutine a single chunk of logic that is 500 lines long? What makes it difficult to keep track of that logic? Just physically, yep. You cannot, I like that. Not at one time. Now, there are many aspects to that all at the same time. Okay, so let me go back to the algorithm that has indentation. See how this indentation is really helpful? But that's only because we can locate the beginning and the end of the same indentation on the same page. So that makes it extra clear, where's the beginning of the loop, where's the end of the loop, where's the beginning of the outer conditional statement, where's the else branch of the outer conditional statement, where's the end of the outer conditional statement, because the beginning and the end of each level is clear. When you have 500 lines of code, can you fit all 500 lines of code on the same page? Even with a super high resolution screen like a 4K and you turn it in portrait mode, it still won't fit 500 lines. Trust me, I've tried. So that means you can't really see the beginning and the end of a construct at exactly the same time. You can see the middle of the code, like, oh, everything is indented all this way, but where is it end? I don't know. Let me scroll up like 20 pages to tell you where's the beginning of that thing. Where's the end? Let me scroll down 10 more pages to show you the end of that thing. So as you're scrolling, you're losing track of where you are. Okay? So that's why we don't want a single piece of code to be too complicated. When I say too complicated, it's easy to define. If it doesn't fit on one page, it's too complicated. I mean, literally. Because if you cannot see it on the same page, you cannot line up the indentation to find out where's the beginning and where's the end. If you cannot see the beginning and the end at the same time, it's too complicated. Is that okay? So that means if you're using a low resolution screen, the definition of too complicated is a little bit different compared to when you're using a larger screen where you can see more at the same time. Okay? But nonetheless, okay, you want to kind of keep your a single piece of logic to be between 20 to 50 lines. Okay, that's kind of the rule of thumb. But nobody can write an operating system or a word processor or anything that's useful in 20 to 50 lines. So how do you fit complicated logic into chunks that are only 20 to 50 lines long each? Yep. Yep, you have to use subroutine, the concept of a subroutine. So what this new slide is talking about, or what this new module is talking about, is really just the concept of a subroutine. But this is called, looking at subroutine from the perspective of kind of more of a scripting language. So I'll give you one example first. This is listing one. So listing one is a little bit different from what we have seen before. This time we have something that's called a subroutine. A subroutine starts with a definition, and the definition starts with define sub or define subroutine. And then the subroutine has a name. In this case, the name of the subroutine is ABC. It has a body, which is line 2, and here's an end, which is end define sub. So that's, in pseudocode, this is how I define a subroutine. In C and C++, there's a different way to define a subroutine. Most scripting languages today have exactly the same syntax as C and C++, so this pseudocode has a kind of unique way of defining what a subroutine is. This code here, this line 4, is the first line that is outside of the definition of a subroutine. And then we have what we call an invocation, so we're invoking a subroutine. And then we have line 6, which is something after the end of the subroutine. So when we want to figure out, but what is being done when this program, the entire thing executes? The first thing it's going to do is line 4, which is the first line outside of the definition of a subroutine. Then it will execute line 5. Line 5 is really special because it's an invocation, otherwise known as a call to a subroutine. So when we say a call to a subroutine or an invocation of a subroutine, it means exactly the same thing. Okay, it's just different words. Yep.
Is it like calling a library? Or libraries and subroutines kind of similar, different? Or?
They're related, they're not the same. A library is a collection of subroutines that is usually provided to you by somebody, like Microsoft or other vendors. Yep.
So say like we have a program that's like a recipe book.
Mm-hmm.
Subroutine would be like a small recipe inside that book, and us
Mm-hmm.
calling it would basically be us.
Yes, C page, blah, 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 of how to, do a certain do a certain step, like how to sear, okay, or how to, I don't know. I mean, I'm not a, huh? So yes, so it's kind of like that, but you have to know when to get back and where to get back to. That is the trick. Okay. Okay. So this is not unlike me reading Wikipedia. Now, I don't know how many of you are addicted to Wikipedia. So when you're addicted to Wikipedia, what does that mean? You look up a page on something that somebody just casually mentioned, but since you're curious, you go like, oh, I want to know what that is. So as you're reading that particular wiki page, it comes across some terms which are hyperlinked because it defines some terms that you need to know first before you can understand the original concept. Then what do? You right-click on it, and then you say, open a new tab. Then you read the sub-concept that you need to understand first to understand the original concept. As you're reading the definition of the sub-concept, what do you encounter? Another hyperlink of something that you do not know yet. So what do you do then? You right-click on that thing, and you go even further, right? So you keep going like this until you get to a particular page that you go like, yes, I understand this entirely. I'm good. Then what do? Ideally speaking. Ideally speaking, you go back to where you came from. So now the question is, how do you know where you need to go back to? Yep.
Oh, I was just saying, is this how you become the master of a craft? You just follow Wikipedia all the way down the line?
And do some of my own thinking.
You go forward.
You go forward.
Yeah, so you would read the one you understood, and then you'd go to the one right before it, and you would read that one until you understood it, and so on, until you reach what you initially searched.
So you have to go all the way to the end, read it, and then you have to back up to what you -1 level, and then continue with that one, and then but that's the concept of a subroutine. But the tricky part is, how do you know where to go back to? Now, when we're talking about browsing, we use tabs to keep track of, which pages are already opened, and more or less, the location where you left off, right? No?
Mine get mixed all the time.
Huh?
I move mine around all the time.
Well, okay, so we are running out of time, so I may not have enough time to fully explain what a subroutine is, but I can explain certain tools that I use when I open up too many tabs and I need to reopen every single tab the same way as before. This is a really cool tool to do it. It's called Session Buddy. Session Buddy. So Session Buddy, and this is another one, it's called Too Many Tabs. And this is yet another one. This one actually is really cool. It kind of shows you hierarchically, which page did you open from which other page. So it can show you, where, how did I get here in the first place, that sort of thing. So I find all of these really, really useful, particularly this guy here. So when you click on Session Buddy, okay, let me show you how useful it is. I'm going to close this browser entirely. And let's see, is that the only instance? Yep, that's the only instance. So I close the browser, and let me reopen it. Now, when I reopen, it doesn't show me all the tabs that I already have pre-opened, okay? Which means, I lost track of, where I was, okay? So this is the next day after that, wiki frenzy, right? Somehow I fall asleep, in the process. So you click on this, tool here, and then you go to this tab here. It automatically saves your sessions periodically, or you can save it manually and give it a name, okay? So you can say, one can be named Anime Frenzy, and the other one is, like Movie Frenzy, and then yet another one is Science Frenzy, and then, MBTI Frenzy, and so on, right? So you can click on one of these, okay, and then you can click Open. And I typically just open it in the same number of windows as before. In other words, it keeps track of which tabs were opened in which window, and it can resume the entire thing of that structure. So I just go ahead and reopen all the tabs, and voila. It reopened all the tabs just like before. And some of these are suspended because I only have 4 gigs of RAM on this computer, and that's not enough to support my expensive browsing habit. So it has an automatic feature. If I have not touched a particular tab long enough, it will put it into suspended mode, so it doesn't use up too much RAM. So yes, I do, but I need the cache to do it too. But it's really helpful, because when you're studying, for different classes, you can have one saved session for a different class. So when you switch from one class to another class, you close the browser, you save it first, you close the browser, you reopen the browser, and then you just pull out the session corresponding to a particular class. It resumes all the tabs for that particular class. So if you're in the middle of doing some research in history for one particular history class, you have all the tabs reopened, back to exactly where you were, before you close that tab, close the browser. So really cool tools that I find useful. Yep.
Do you feel that it's more complicated to go through your browser history and open everything back up?
Oh, that is way too slow. Yeah, this is so much faster.
I didn't think how fast your computer was. Is it just slow because of your computer?
Yeah, this computer is really slow. It has a 2nd generation i5, and we're talking about a mobile i5, so they're actually slower than most other. You can actually tell how fast it's running. So right now it's at 2.19 gigahertz, but because it's an older i5 processor, it doesn't do as much work per clock compared to a 8th generation i5.
May I remind you that I have no idea what you just said?
That's okay. That is perfectly okay because it's all recorded. So now you can go home and open up like tabs to find out what I just said. Or you can ask Alexi or Google and just say, what did Tech just talk about? Yeah, I might need a partnership with Amazon so that Alexi can answer questions about the classes, right? Alexa, yep. As you can see, I don't need to use Alexa at home. All right. Well, I'll see you guys on Wednesday, and remember that's exam one day, so be prepared.